Welcome back, focused learners. Let's jump right into today's explainer. We're looking at a story that's part tragedy, part redemption, and all about the internet's invisible infrastructure. It's called Heartbleed, and it literally shook the foundation of digital security to its core. Just to give you an idea of the sheer panic that hit the cybersecurity world back in April 2014, listen to what security expert Bruce Schneier said at the time. Catastrophic is the right word. On the scale of 1 to 10, this is an 11. This wasn't just another routine bug update. This was a massive, existential threat to online privacy. Okay, let's dive into this. 500,000. That's the estimated number of vulnerable servers worldwide when this exploit was publicly disclosed. And we're not talking about tiny, forgotten blogs here. We are talking about the absolute titans of the web: Google, Amazon, Facebook. Their servers were essentially left wide open. Section 1. Anatomy of a bug. A technical misstep. Let's look at exactly how this happened. So to really grasp the magnitude here, we have to look at the microscopic coding error that started it all. It involves a foundational concept known as the heartbeat extension. Now, this is a TLS or DTLS protocol feature inside the super common OpenSSL cryptography library, and its job was incredibly simple. It just allows a computer to send a short string of data to check if the other end of the connection is still alive and listening. Basically, it keeps the connection active without having to constantly transfer heavy data back and forth. But what's really fascinating here is the sheer simplicity of the exploit. Normally, an intended heartbeat works kind of like an echo. I send you a short word and you echo that exact word back to me. But with the Heartbleed exploit, the attacker simply lies about the length of the word. They send a tiny one-letter word, but they claim it's actually 64 kilobytes long. And the server, totally tricked, grabs that single letter, and then it just scoops up the remaining 64 kilobytes of whatever happens to be sitting right next to it in active memory and sends all of it back. And this massive data hemorrhage happened because of literally one missing line of validation code in the C programming file. The code allocated memory based entirely on the user's claimed payload size, completely failing to validate if the actual string matched that length. The result? An attacker could read up to 64 kilobytes of uninitialized heap memory per request. And because this attack left absolutely zero trace, threat actors could just sit there, repeatedly siphoning off memory, quietly grabbing private keys, passwords, and user data, just draining the server 64 kilobytes at a time. Section 2. Hijacking the system, bypassing MFA. Let's talk about how this played out in the real world. As soon as the bug was publicly disclosed, the chaotic fallout was immediate. Just look at the unprecedented spike in revoked security certificates. IT departments everywhere were in a total panic, frantically racing to revoke and replace compromised certificates. Why? Because their private encryption keys were potentially exposed to literally anyone with an internet connection. And yes, threat actors were absolutely taking advantage of this. A Mandiant incident report laid out exactly how an attacker bypassed strict corporate security using this exact flaw. Step 1. The attacker sends repeated malformed heartbeat requests to an organization's SSL VPN server. Step 2. They steal active session tokens straight from the VPN's exposed memory. And Step 3. Armed with those stolen tokens, they just hijack the active session. They completely bypassed multi-factor authentication because as far as the server knew, they had already legitimately logged in. Incredible, right? If bypassing MFA wasn't scary enough, Cloudflare actually set up a challenge server to see if the absolute worst-case scenario is possible. Could someone actually steal the crown jewels, the server's private encryption keys, using just this exploit? Well, the answer was a terrifying yes. 2 researchers independently proved they could extract the private keys just by sending millions of requests until the key fragments finally showed up in the memory dumps. No other hacks required. Section 3. The culture of bad code. Systemic failures. So, how did this happen? Why was such a critical piece of the internet's architecture so incredibly fragile? Well, the root of the problem becomes pretty clear when you look at the software metrics for OpenSSL version 1.0.1. That's the version where Heartbleed lived. It suffered from massive code bloat, over 272,000 lines of code, and extremely poor comment density. Over the years, the code just grew and grew, while readability and maintainability drastically shrank. It was a mess. It really was the perfect storm of systemic failures. The development team had this Spartan C programming culture that actively prioritized terse, compact code over clear readability. And worse, there was a severe lack of funding. I mean, this crucial piece of global infrastructure had exactly one full-time developer. Just one. Plus, the design lacked compartmentalization between TLS and DTLS, meaning a vulnerability in one compromised both. And to top it all off, many organizations had this false sense of security because a specific OpenSSL object module was FIPS 142 compliant. They blindly trusted that the rest of the unaudited code was equally secure. Now, because this bug sat undiscovered for 2 whole years, public speculation absolutely ran wild. Security experts openly wondered, did intelligence agencies deliberately insert this bug for unfettered access? Or was it just an accidental flaw they found and silently exploited? We're impartially reporting the facts from our sources here, and there is no definitive proof either way. But the mere fact that this public debate happened at all really highlights the immense geopolitical stakes resting on this single piece of open source code. Section 4. The open source paradox. The healing process. So out of this total catastrophe came a massive, somewhat paradoxical healing process for the digital world. If you contrast those bloated OpenSSL metrics we just saw with LibreSSL, which was a fork created immediately after Heartbleed by the OpenBSD team, the difference is staggering. In its very first week, the LibreSSL team aggressively cleaned house. They purged roughly 90,000 lines of C code, just to make the library auditable, understandable, and ultimately far more secure. Heartbleed served as a massive wake-up call for the original OpenSSL project too. Suddenly, millions of dollars in new, desperate funding poured in from tech giants. They finally hired multiple full-time developers, and a major refactoring effort kicked off to modernize the totally neglected codebase. Section 5. The silver lining. Measuring security. This leads us directly to a really fascinating look at how we actually measure security. If you look at bug discoveries, there was a predictably low number before Heartbleed, right? But then there's a massive spike. 91 new vulnerabilities discovered shortly after. Now, this feels completely counterintuitive, but finding more bugs actually meant the internet was getting safer. It didn't mean OpenSSL was getting worse. It meant researchers and developers were finally actually looking at the code. Ultimately, OpenSSL adapted. It transformed from a neglected monoculture into a model for open source resilience. After Heartbleed, commits per month tripled. Overall code complexity decreased significantly. They even earned a Core Infrastructure Initiative Best Practices badge. It proved a huge, vital lesson for the software engineering world. Vulnerability count alone does not equal insecurity. An active, well-funded project that aggressively hunts down and fixes its flaws is vastly superior to a silent, unaudited one that's just hiding a ticking time bomb. Which brings us to the end of our explainer, and I want to leave you with this provocative thought. If it took a global disaster of this magnitude to adequately fund and fix something as critical as OpenSSL, what other foundational code is just waiting to bleed? The digital world we rely on every single day is built on layers of invisible, often wildly underfunded infrastructure. The question isn't if another bug is out there, but when we'll find it and whether we'll be ready.